Hey there, all my cool cats and kittens. Today we're going to learn about inscribed angles. See, we already know about this dude called a central angle. And he is the one, or she, it is the one that has a vertex on the center of the circle. And that would be like angle AQB up here. This right here is a great example of a central angle. So angle AQB is a central angle. And what we know about the central angle, it's equal to whatever its intercepted arc is. So it would be equal to arc AB. So central angles are old. We're not doing those today. Today we're going to be learning about inscribed angles. Woo! Inscribed angles, they're going to have their vertex on the circle. So with the inscribed angle, we're looking for a vertex on, let's go with capital on and underline it, on the circle. And that means this guy right here, ACB, vertex C, and C is lying right on the circle. So angle C, or angle ACB, if you want to call it by its full name there, angle ACB would be an inscribed angle. Is an inscribed angle because it has its angle on the vertex. And what we're going to learn about these dudes is that they are equal to half of the arc. So instead of being equal to exactly AB like central angle, it's a little bit different. It's going to be equal to half of AB. So I could get into the math. I could do that real quick if you want me to. I could do it. Or you could take my word for it. So if you don't want to listen to me, don't listen to me for this next little part. But know that it's equal to half of that intercepted arc. So let's say that, I don't know, say that arc is 80 degrees. Well, this angle is going to be half of that. It's going to be 40 degrees. That's how inscribed angles work. Alrighty. So just real quick, I'm going to explain why it's half. The reason that it's half is because, let's see. Say we don't know this angle. Well, let me erase what's already there. Let's say Say I don't know this angle here. It's question mark. And this is a question mark. I know that if this little segment right here, segment QC is a radius. Hey, segment QB is also a radius. So that makes that triangle here an isosceles triangle. And isosceles triangles not only have two congruent legs, but they also have congruent angles. So I know that those two question marks are exactly the same because they're the base angles of that isosceles triangle. So this angle is congruent to this angle. Put my little congruent mark there. I should erase some of the mess. Get out of here, mess. So my congruent marks show that those two angles are congruent to each other. Nice. Now something else we learned about triangles back in the day is we learned that this exterior angle here is going to be equal to the sum of the remote interiors. Remote interiors would be this angle here and this angle here. So I know that that angle AQB, that exterior angle, is going to be equal to the sum of, and I could call this angle C here, I'm going to call it QCB. And this angle B here would be QBC. So I know that's true because the exterior angle is equal to the sum of the remote interiors. That's some like semester 1 stuff. So I know that those two are the same. This angle and this angle are the same, so I could use some substitution. In fact, let's say that because measure of angle QCB is equal to the measure of angle QBC, they're interchangeable. So up over here, I'm going to replace, instead of saying two different angles, I'm going to say 2 times the measure of angle QCB. Because they're identical, and there's 2 of them, equals the measure of angle AQB. Now we know that the measure of AQB is the same thing as the arc AB. So I can replace this because the measure of angle AQB is equal to arc AB. I can substitute and I can replace that with arc AB. And lastly, I can divide by 2 to get rid of that, so the division property. And my final result here would say half of arc AB is equal to the measure of angle QCB. So that's how we can prove that the inscribed angle is equal to half of the arc. Or you can just say, hey, the inscribed angle always equals half of the arc. Or shoot, you could say that the arc equals 2 times the inscribed angle. All right, I know I made that way more confusing than I had to, but the moral of the story is make sure you know what a inscribed angle is and how it's different than a central angle, and also make sure you know how to find the measure. So you just divide the arc by 2. Alrighty, so let's take a look at some of the properties of these inscribed angles. All right, so here's a theorem and its converse. We already know that the measure of an inscribed angle is half of the intercepted arc. We just kind of proved it. So here's 3 cases of when you might see an inscribed angle. First one is, well, you know it's an inscribed angle because the vertex is on the circle. So I know, if I just made some numbers up here for you, if I said that RT was 42 degrees, then you know that this angle, this inscribed angle, is going to be half of that arc. Angle S equals half of RT. So that's how inscribed angles work. So if the arc is 42, because that's the number that I made up for you, then half of 42 equals the measure of angle S. So the measure of angle S must be half of 42 is 21 degrees, according to the numbers that I made up there. So that's all you do, and that's all you do in all 3 of these situations. Now, sometimes you're going to see the converse. They're going to throw the inscribed angle at you. They're going to be like, hey, dude, this inscribed angle is like 48 degrees, man. And then you're going to have to figure out what the intercepted arc is. So you know that half of the arc equals the angle. The inscribed angle, right? So I know that half of RT is equal to 48. So that means if I want to do algebra here, I could just multiply it by 2 and know that RT, that arc, is equal to 48 times 2, 96 degrees. And you can check your work by saying, hey, is the angle half of the arc? Yes, it is. Okay, so that's that converse where the arc is double All right. So again, if this is a 32-degree angle, then I know that the arc is double. So I could just jump straight to saying, hey, arc RT must be 64 degrees. All right, guys, so hopefully you see how this is different than central angles. Central angles were easy. It was just the same number. But this guy, you either have to half if you're trying to find the angle, or double if you're trying to find the arc. So I've got some more examples of that you're going to do later. And let's look at some more theorems. Yay, theorems, theorems, theorems. These are corollaries. They're theorems that go along with the original theorems. And the first one is when you have two inscribed angles that share a common intercepted arc. So here's the example down here, corollary 1. I've got this inscribed angle, RSU, and its intercepted arc would be this RU, arc RU, and then I've got this other intercepted arc, inscribed angle, my bad, and its intercepted arc is also RU. So they both share the same intercepted arc. That means that those two angles must be the same. So whatever S is, angle S here, angle T is going to be the exact same. So that's what's going on there. And a lot of times they throw some algebra in there. After you say that angle S is congruent to angle T, then they tell you like, hey dude, angle S is like x plus 7, and angle T is like, I don't know, 3x minus 4. I don't know, I'm just making things up. And then you have to know, oh yeah, they're congruent. They're congruent, so they're equal to each other. So that means that x plus 7 must be equal to 3x minus 4. And I just made stuff up, but that's something you could do with this, questions that you might see in the future. Then you would have to use your algebra skills to solve, and you could figure out what x is and what each of these angles is going to end up being. So that's something you could end up doing. Number 2, an inscribed angle measuring 90 degrees has an intercepted arc. That's a semicircle. Okay. And also, if a triangle isn't... Oh, yeah, here's the big one. This one's cool. If a triangle is inscribed, and then one of the sides happens to be the diameter, you might notice that RS here is the diameter. Well, that means if I have that triangle and I'm using the diameter, anytime you use the diameter when you're inscribing a triangle, that means it's going to end up being a right triangle. And the reason for it is because that's the diameter, I know that this piece is a 180 degree chunk of circle. And if that chunk is 180 degrees, then the inscribed angle that goes with it, which is angle T, must be half of that. Boom, 90 degrees. Okay, but what I want you to know also is that anytime you have a triangle inscribed and you're using the diameter for one of the sides, it's going to be a right triangle. And then lastly over here, corollary number 3, if I've got a quadrilateral, then the opposite angles, so angle R and its opposite angle, angle T, I put different congruent marks because they're not congruent to each other, so you can see there's a different amount. They're going to be supplementary. They're going to be supplementary. And the reason for that is because together, the intercepted arcs, their intercepted arcs together would add up to 360 degrees. So if their arcs add up to 360 degrees, then the angles are going to add up to half of that because they're inscribed and they're half of the arcs. So opposite angles like angle R and angle T are going to be supplementary.